Okay, previously we had completed two parts of atomic structure. One is discovery of the fundamental particles. The next important part is atomic theories like Thomson atomic model, Rutherford's atomic model. Now we are moving to the next part, that is called as atomic number. It is denoted by Z. Atomic number was discovered by a scientist named as Moseley. In an atom, atomic number is equal to number of electrons, that is also equals to number of protons. In an atom, atomic number always equals to number of electrons, and it is also equals to that of number of protons. Thus, this is one of the important fundamental property of an atom. Just like fingerprints of two different persons cannot match together, in the periodic table, different elements are having different atomic numbers. So this is one of the important criteria for arranging elements in the periodic table, and it was proposed by Moseley. After the discovery of atomic number, new inventions were observed in the field of chemistry in the earlier 20th century, in which the first important discussion we are going to do now is isotopes, isobars, and isotones. Isotopes, isobars, and isotones. Atoms of the same element having same atomic number but different mass numbers are called as isotopes. Atoms of the same element having same atomic number but different mass number, that will be called as an isotope. In a symbol of an atom, how can we identify atomic number and mass number? So this is atomic number indicated by Z, and this is called as mass number indicated by A. And very important, A is equal to Z plus N, nothing but number of protons plus neutrons present in the nucleus of the atom is called as mass number. And from this, to find the number of neutrons, we had A minus Z. Here A is called as mass number. Z stands for atomic number. N stands for number of neutrons. Thus we had three important relations here. Number of protons is equal to Z, number of electrons is equal to Z, number of neutrons is mass number minus atomic number. When a symbol is given like this is called subscript and this is called superscript. This is denoting atomic number indicated by Z. This is denoted by A, nothing but mass number. Now when we are discussing the first definition called as isotopes, atoms of the same element having same atomic number and different mass numbers are called as isotopes. In all the cases, we will find same number of protons. We also found same number of electrons, but isotopes differ in number of neutrons, because in the first case Neutrons are 1 minus 1 0. Here 2 minus 1 1. Here 3 minus 1 2. The first isotope of hydrogen is protium. Second isotope is deuterium. Third isotope is tritium. The lightest isotope is called protium, indicated by H11. Heaviest isotope is denoted as H12, called as deuterium. And H13 is a radioactive isotope. Means the isotope which can emit alpha, beta, gamma radiations, that will be called as radioactive isotope. Thus, isotopes are having same atomic number, but they differ in number of neutrons and also differ in mass number. So, this concept is very important because we had so many questions in class 8th book as well as class 7th book based on calculation of number of fundamental particles. Now, next, if we consider the second important definition, that is called as isobars. Atoms of different elements having same mass number, that is called as isobars. Atoms of different elements having same mass number are called as isobars. For example, if I take argon 1840, potassium 1940, calcium 2040. Here, this is superscript is mass number, this subscript is atomic number. So all these three contain same mass number 40, 40, 40. But they differ in atomic numbers. Thus, isobars are having only one property same, that is mass number. Whereas isotopes are having only one property same, that is atomic number. Means protons are same, electrons are same. Now, the third one is called as isotones. Atoms of different elements having same number of neutrons are called as isotones. For example, if I take carbon 614, nitrogen 715, oxygen 816, in all the cases number of neutrons are 8, because number of neutrons here A minus Z means mass number minus atomic number. So, the atoms which are having same number of neutrons are called as isotones. Thus, we should give a simple idea for the students. Isotopes are having same atomic number. Isobars are having same mass number. Isotones are having same number of neutrons. Isotopes are the properties of identical atoms, whereas isobars and isotones are properties of different atoms. Next, we had one more important discussion, isoelectronic species. The molecules or ions which have same number of electrons are called as isoelectronic species. The molecules or ions having same number of electrons are called as isoelectronic species. For example, if I take CO, this is called carbon monoxide, it is totally having carbon contains 6 electrons, oxygen contains 8 electrons, totally it has 14 electrons. If I take N2, means dinitrogen molecule, it has 2 into 7, 14 electrons. So these two are having same number of electrons, and I can take one more example, Cl minus. Carbon contains 6 electrons because atomic number is 6. Nitrogen contains 7 electrons. Here minus indicate 1 electron was gained. In case of an anion, electron was gained. Therefore, I need to write +1 here because the charge here is -1. Here also we are getting 14 electrons. So all these three are having same number of electrons with the same number of atoms. 2 atoms. Here also 2 atoms. Here also 2 atoms. Such species are called isoelectronic species. So we had so many numericals based on this topic, especially calculation of total number of fundamental particles. We will take an example. If the question is calculate total number of fundamental particles in tritium. This is called as tritium H13. I would like to find total number of fundamental particles. So this is atomic number. This is mass number. First of all, number of protons is equal to Z, that is 1. Next, number of electrons also equals to Z, that is 1. Next, number of neutrons, that is equal to A minus Z, that is 3 minus 1, that is 2. And total number of fundamental particles. Total number of fundamental particles will be the sum of electron, proton, neutron here, that we can take directly as A plus Z, that is 3 plus 1, that is going to be 4. If we add protons, electrons, neutrons, sum also, you will be getting 4. Thus, in a neutral atom, to find the number of electrons is Z, number of protons is also Z, number of neutrons is A minus Z, and total number of fundamental particles is A plus Z. This is about one of the important radioactive isotope of hydrogen called as tritium. Now, after this, we need to discuss about the nature of light. Light has two important characteristics: wave nature and particle nature. Particle nature of light was proposed by Newton, which is also called corpuscular nature, whereas wave nature of light was proposed by Huygens. Then what are the important wave characteristics that are associated with light? The first important property is wavelength. This is denoted by lambda. When we consider a propagation of wave like this, the distance between any two successive crusts or any two successive troughs, that will be called as wavelength. The distance between any two successive crusts or any two successive troughs, that is called as wavelength. It is denoted by lambda. The units of wavelength is, it is expressed in angstroms or nanometers. For the children, conversion of angstroms to centimeters and meters is very important in attempting the problems. So we had 1 angstrom is 10 power minus 8 centimeters or 10 power minus 10 meters. 1 nanometer is 10 power minus 7 centimeters or 10 power minus 9 meters. This is an important conversion for angstroms and nanometers related to centimeters and meters. This is a first important wave characteristic. Now the second property we are going to discuss for the wave is frequency. Frequency. It is denoted by nu. The number of waves that cross a fixed point in 1 second. The number of waves that cross a fixed point in 1 second, that is called as frequency. For example, frequency is denoted as c by lambda, where c is velocity of light, lambda is called as wavelength of radiation. And for frequency, units are H, or it may be cycle per second, or it may be second inverse. There are three important units for frequency: H, cycles per second, and second inverse. But nowadays the most widely used unit for frequency is second inverse. One of the old unit widely used is cycles per second. So this is about frequency. It is the number of waves that cross a fixed point in 1 second. Then our third property we are going to discuss now is wave number. This is denoted by nu bar. The number of waves extended in unit length, means either in 1 centimeter or in 1 meter, that will be called as wave number. So wave number is denoted as 1 by lambda, and its units are centimeter inverse, or you can also consider meter inverse. Nu bar is equal to 1 by lambda. It is the number of waves extended in unit length, either in 1 centimeter or in 1 meter. Now we will discuss about relation between frequency and wave number. As you know, frequency is c by lambda. Instead of 1 by lambda, here we can write c into nu bar, because 1 by lambda is changed as nu bar. Thus we can write nu is equal to c into nu bar. Means, important statement here, the product of velocity of light and wave number of radiation must be equal to frequency of radiation. Thus frequency is depending on wave number. Frequency depends on wavelength also. Next, the next important property for the wave is amplitude. It is the displacement of the wave from the mean position that will be called as an amplitude. The displacement of the wave means it may be either height of the crest or depth of the trough, that will be called as an amplitude. The displacement of the wave, this is called as a mean position, horizontal line. The displacement of the wave from the mean position is called as amplitude. This is an independent wave property because it is not depending on wavelength, frequency or wave number. Next, other important property is energy. Energy of a wave is equal to h nu. Means E stands for energy of the wave, h stands for Planck's constant, nu stands for frequency of radiation. And here I can write in the place of nu c by lambda. In the place of 1 by lambda, I can write nu bar. Thus, energy related to other wave characteristics like this. E is equal to h nu or hc by lambda or hc nu bar. From this I can write E is directly proportional to nu, E is inversely proportional to lambda, E is directly proportional to nu bar from this equation. Thus, in the numerical problems, I can write ratio of two radiations having different energies as nu 1 by nu 2. Here E1 by E2 is equal to lambda 2 by lambda 1. Here E1 by E2 is equal to nu 1 bar by nu 2 bar. These are the three important relations for wave characteristics related to energy of the radiation. Energy of a radiation directly proportional to frequency. Energy of the radiation directly proportional to wave number. Energy of the radiation inversely proportional to the wavelength. Thus, problems based on these formulas are most repeatedly given in our practice materials of class 8th and class 7th also. So, these are very important relations for wave characteristics. Now, the next part we are moving now is Planck's quantum theory. Because to understand the structure of an atom, we require this theory called quantum theory. This was proposed by Max Planck. So according to this theory, the first important postulate is the emission or absorption of radiation is due to the vibration of the charged particle. The emission means release of light. Absorption means taking of light. Means from a body either energy is emitted or absorbed due to the vibration of the charged particle. Energy emission or absorption does not take place continuously. It takes place discontinuously in the form of small packets called as quanta. According to Planck, small energy bundle of energy or small bundle of energy, that will be called as quanta, that is denoted as E is equal to h nu. This is called as energy of quanta, and here h is called as Planck's constant and its value is 6.625 into 10 power minus 27. Units are erg second in CGS system, or it is 6.625 into 10 power minus 34 joule second, that is in SI system. Thus, according to this theory, energy is emitted when a particle moves from higher levels to the lower levels. Energy is absorbed when a particle moves from low levels to the higher levels. And one of the very important point here is emission or absorption of energy always takes place in integral multiple of quanta. What is meant by integral multiple? For example, if I take delta E, that is E2 minus E1, that is equal to NH nu, where n have integer values like 1, 2, 3, 4 except 0. Means when a particle moves from one level to other level, energy may be emitted or absorbed always it will be in integral multiple of h nu. Means emission or absorption of energy always takes place in the form of 1 h nu, 2 h nu, 3 h nu, 4 h nu and so on. Thus, when fixed values of energy packet is available, such a phenomenon is called quantization of energy. So, Planck's quantum theory first time proposes quantization of energy, means emission or absorption of radiation always takes place in integral values like 1, 2, 3, 4. Fractional values are not allowed. Such a phenomenon is called quantization of energy. This theory is mainly proposed to explain black body radiation. Black body is a body which can act as a perfect absorber and perfect emitter of radiant energy. It is a hypothetical body, black body. It is a perfect absorber, means it absorbs all the radiation falling on it, as well as it is a perfect emitter of radiant energy. But practically there is no ideal black body exist in nature. But this theory is completely based on explanation of black body radiation. One of the important point from this theory we can take is quantization of energy. That is, emission or absorption always takes place in integral multiple of quanta. And energy of quanta is E is equal to h nu, and the small energy packet in this theory is called as quanta. However, this theory was extended to all electromagnetic radiations by a scientist named as Einstein. Einstein extended Planck's quantum theory to all electromagnetic radiation. So, what is meant by electromagnetic radiation? The radiations associated with both electric and magnetic field strengths are called as electromagnetic radiations. For example, the signals we are receiving for our cell phones and the signals for television screens all are nothing but electromagnetic radiations. Some of the important examples of electromagnetic radiations are gamma rays, X-rays, UV rays, means ultraviolet, visible, infrared, microwaves, radio waves, which plays a very important vital role in our daily life. For example, the light coming from the electrical bulb are visible to our naked eye, hence they are called visible rays. Generally, the wavelength range for visible rays lies in between 3800 to 7600 angstroms. All electromagnetic radiations have so many uses in our daily life, and these are electromagnetic radiations. Some of them can be produced by artificial methods, some of them are available in the nature. For example, the radiations coming from the sun mainly consisting of infrared radiations. So this is one of the important points regarding quantum theory proposed by Planck, called as Planck's quantum theory. Why we discussed this theory is in a way to understand most important model of an atom called as Bohr's theory. A student should have idea about this Planck's quantum theory as well as Rutherford's atomic model. Now we are moving to the next very important topic of this atomic structure called as Bohr's atomic model, because atomic structure is not going to be completely fulfilled, teaching is not going to be fulfilled with satisfaction for a lecturer or teacher without explaining this topic called as Bohr's atomic model, because this theory had led a great development in the field of chemistry in atomic structure. So even though it was proposed at earlier 20th century, till now this theory is a very important theory in this chapter. Now we are going to discuss now about Bohr's atomic model. Okay, Bohr's atomic model was proposed by Niels Bohr. This theory is based on drawbacks of Rutherford's model, and it is based on the important postulates of Planck's quantum theory. So according to this theory, atoms revolve around the nucleus in circular paths called as orbits. These are also called as shells. These are also called as main energy levels. These are denoted as n is equal to 1, 2, 3 from the nucleus. They are also denoted as K, L, M and so on. Here n is called as principal quantum number. So Bohr's model introduces principal quantum number. This denotes circular orbits around the nucleus which are at fixed distance, means their distance doesn't change. Electrons will be revolving around the nucleus, and these orbits are also called as stationary shells, because the energy of electron does not change as long as it revolves around the nucleus. The energy of an electron in a circular orbit is always fixed. Energy of electron changes only when it moves from one orbit to the other orbit. In an orbit, energy does not change. That's why these are called stationary orbits, because the energy of electron in a given orbit is always fixed. Next, according to this theory, product of mass into velocity into radius. What is meant by radius? The distance between the center of nucleus of an atom and electron present in an orbit, that is called as radius. If I measure the distance between the center of nucleus and electron present in orbit, that is called radius. So the product of mass of electron, velocity of an electron and radius of an orbit, this is called as angular momentum. So the angular momentum of revolving electron in a circular orbit is also quantized, means it is going to have fixed allowed values. Thus angular momentum is equal to nh by 2 pi, where n is called principal quantum number. For example, if I take K shell as n value is 1, angular momentum is mvr is equal to h by 2 pi. If I take L shell, angular momentum is equal to 2h by 2 pi, because n value is 2. If I take M shell, angular momentum mvr is equal to 3h by 2 pi. So on simplifying this, I may get h by pi in second case, here 1.5 h by pi. Thus very important, angular momentum is a function of h by 2 pi, which is going to be always integral multiple, means n value is always fixed, that is 1, 2, 3, 4. Remember this very important point, quantization occurs at two places in our discussion here. Quantization of energy was proposed in Planck's quantum theory, means energy is emitted or absorbed always in fixed quantities or integral multiples of h nu, and here also the angular momentum of electron is always fixed, means it is allowed to have fixed values like h by 2 pi, h by pi, 1.5 h by pi, etc. So many questions based on this topic were given in class 8th book of our material. So this is a very important area for the students. And there is one more very important point in this theory. When electron jumps from higher orbits to the lower orbits, means for example 5 to 1, 4 to 1, 3 to 1, etc., energy is emitted. So the energy emitted or absorbed, as you know, energy is absorbed when electron moves from lower orbits to higher orbits. Two cases of electronic transition. Electron may move from lower orbits to higher orbits, called as excitation. In that process energy is required. And electron can move from higher orbits to lower orbit, called as de-excitation, in which energy is emitted. Thus delta E is energy difference, that is equal to E2 minus E1, that is energy of higher orbit minus energy of lower orbit, that will be equals to, again this is equals to h nu, where h is Planck's constant and nu is frequency of radiation, and this is also quantized, means here energy emitted or absorbed always takes place in integral multiple of h by, that is h nu. So two important points here. Generally when we are discussing Bohr's atomic model, most of the teachers and what they do is they will teach more number of problems, because in this chapter we had so many applications based on problem, but theory is very important here. What factors are quantized, that is a very important factor to be learned by the students here. So first of all, we should make the student conceptually strong. Thereafterwards we have to teach them in problematic part. Otherwise if you teach more number of problems ఎక్కువగా చెప్తే, they may be good in problems, but in the exam the same numericals may not come, so students may not get good marks. But if you make students conceptually strong, then he will be developing his knowledge. So whatever type of question comes in the exam, he can do the question. So that's why these two theories in atomic structure, that is Bohr's theory, Rutherford's theory, Planck's quantum theory, are very important in understanding the structure of an atom. This theory has some merits as well as demerits. The first important merit is it could explain the spectrum of hydrogen.